Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one is about successive oblique impacts with a plane surface or surfaces. Let's look at a picture first which shows the general picture. We're talking about an oblique impact, in other words the incident velocity is not perpendicular to the plane. We will, however, stay in two dimensions, so the motion is as a whole is in a plane perpendicular to the fixed plane. Now, although the plane's fixed, we can still deal with that by Newton's law of restitution. It's just that one of our two colliding objects has got zero velocity before and afterwards. But we apply Newton's law of restitution in that case along the perpendicular to the fixed plane in the plane of motion. And the speed parallel to the plane is unchanged. That's the velocity component strictly is unchanged parallel to the plane. That's because it's smooth and there can't be any impulse in that direction. So we'll need a set of axes like that in order to work with vectors, and in general we'll have an incident velocity denoted there by components u and minus w. Minus because with that picture and the axes I've drawn, then you'll have the w value, the component that's up and down will actually be downwards, and hence I've shown it as minus w. There'll be corresponding final velocity with two components, and you notice that the second one, the lower one, is the same as the lower one of the final velocity is the same as the lower one in the incident velocity, and that's because of the conservation of momentum component parallel to the wall. We'd expect that u and v will be related by the restitution law. In other words, that v is just equal to eu. Right, well there's our situation, the problem with as yet to be solved. Now we should start off by looking at the set of axes to get our notation for vectors specified. Then we'll have the incident velocity shown. That's resolved into u sine theta and u cos theta using the theta between the incident line and the wall. That will give rise to a bounce back velocity. Notice that the second component is unchanged compared with the first. The second component of each, perhaps I should say, is unchanged because that's the conservation of momentum component along the wall, whereas the u sine theta is multiplied by minus e to get the corresponding component in the second case. If we do that again, we'll get the final velocity, but first let's just step aside and ask what happens if the coefficient of restitution is equal to 1. Now in that case what we've got will be just the same to start with, but in the second case we can replace the e by minus 1. So far that doesn't give any obvious resonances, but if we apply e equals 1 to the second case, notice this time it's the lower component that's multiplied by minus 1 and the upper one that's unchanged. Now compare the final velocity with the first velocity, and you can see that the two are exactly the same except that one has a minus sign in front of it. That means that in this setup the incident velocity is exactly reversed by that kind of impact. So there won't be any loss of energy because the speed is essentially unchanged. It's just that the direction considered as a velocity is reversed. Right, back to the problem we'll be considering. We've got an incident 60 degrees there, and we've got a coefficient of restitution, and we've got a right angle here. I didn't say that, but that's assumed. The two walls are at right angles. So let's take diagrammatically that information so that there's more room for the calculations. Nothing's changed there, simply the essentials have been retained. So we resolve the first vector speed, the vector velocity I should say, u, into two components, u sine 60 and u cos 60 using the 60 degrees. And remember that sine 60 is root 3 over 2, cos 60 is a half. When we apply the two principles of conservation of the momentum component along the wall and restitution perpendicular to the wall, we'll get a new pair of velocities like that. It's the first one that's multiplied by the coefficient of restitution and the second one that's unchanged. That's simplified, and you'll note that these two components actually have the same magnitude, and that would imply that this angle here is 45 degrees. That's not strictly relevant to the calculations, but an interesting observation. Now we have to use the same principles at the second collision point. This time the roles will reverse. It will be the second one that's multiplied by the coefficient of restitution and the first one that's left unchanged. So when we come to calculating energy, we're going to have the initial half mu squared minus, in the second case you're going to have a factor u, so we can write a half mu squared, but you're going to need the Pythagorean calculation on the components. There'll be a half squared and there'll be 1 over 2 root 2 squared. Now that is essentially the energy loss. I've got there the initial energy minus the final. Normally you do it the other way around, but in anticipation of a loss, that's what you would get. But first we're asked to calculate the velocity, and we've got that. It's that answer there. So now we can move on to calculating the percentage change of the kinetic energy as I've just outlined. And we've got the information on the diagram for that, so we'll put it diagrammatically like that. Now the energy calculation I outlined is going to be those two differences. There you are, and I've put it so that the smaller one comes second in anticipation of a positive answer, and it's all got to be divided by the original kinetic energy, half mu squared, so that the answer is positive. Now that looks pretty horrendous, but in fact the half mu squared is a common factor in the three different terms, so we'll end up with just a 1 instead of the half mu squared, and we'll end up with just this expression for the second one. So this one will become a 1 and the other one will be those two brackets worked out. So there we are, the 1 minus, and the bottom's calculated cancel to just a 1. So this is a quarter, this is an 1/8, so it's 1 minus 3/8, which gives us 5/8. So on the basis of that we can say that 62.5% of the energy is lost. Well, that brings us to the end of this particular video, and the next one is on oblique impacts, where it's not a fixed surface but a stationary sphere.